Hi, I'm Ben-Yaakov. This presentation is entitled Linear Optocouplers and Application. We need linear amplifier in a number of situations. For example, if we like to measure the voltage drop on a sense resistor for measuring current, then we need a isolated amplifier because usually this side will be floating on some potential, some voltage, while we like to have the output referred to ground. And there is, of course, another very important example is the case of a power supply in which we have an isolated output which has a different ground than the input at the power stage. And then we need a feedback from the output to the power stage. In this case, we need isolation such that we'll have two different ground and the signal for the feedback is going through this isolated part. So there are many applications, many other applications in which we need a isolation between input and output. And in this presentation, I'm focusing on a linear amplifier, which is isolated. Now, the conventional optocoupler is, you might say, also a isolated amplifier. We have a current coming in into the LED, and then we have the phototransistor, which generates an output, and it's isolated through the light. But this arrangement is extremely nonlinear and very temperature sensitive, so you cannot consider it as a linear amplifier or linear transfer function. It's highly nonlinear. Yet it has many applications. I'll discuss it later on, but this is not a linear transfer function or linear amplifier. On the other hand, we have here a device which has a LED, it's a light emitting diode, like a regular optocoupler, but then it has two photodiodes, in this case shown as photodiodes, actually it could be phototransistors, and the same light or same fraction of light is actually impinging on these two light detectors, that is the photodiodes here. Okay, so this is an arrangement in which you can then build around it a linear amplifier. Now, one of the advantage here is that it has a very high gain stability in terms of temperature. It's also very linear, and the gain stability is in the range of 0.05% per centigrade, which is, of course, very good. Now, when it comes to pairing a LED and a photodetector, there are actually three ways of managing the signal. One is the so-called photoconductive arrangement, in which the photodiode, is reverse biased, and then when the light is impinging on the junction, then charged carriers are generated, and therefore you'll have a current, which is a function of the current passing through the LED. There is another arrangement in which you measure the voltage across this photodiode. This is the equivalent circuit of a photodiode. This current source represents the generation of the charge carrier due to the light. And then, of course, you have a voltage, which is a function of the light, and which is a function of the current through the LED. This, however, is not very linear, also highly temperature dependent, so this is not used usually for detection and signaling. While the third one, which is the current source arrangement, is very good and it's used a lot. In this case, we take the diode here and actually we clamp it to zero. So there is a zero voltage across the diode. So thereby, we're actually capturing all the current here through this resistor to maintain this virtual zero here. So the condition of the voltage is not changing as the light is changing or the current is changing. So this is a better solution. However, it turns out that the bandwidth of this arrangement is usually smaller than the bandwidth of this arrangement. So if you are interested in a high bandwidth, this could be a better choice. So this is how you process the signal that is coming out of the LED, which is a function of the current through the diode. Now, around this linear optocoupler, we can build a linear isolated amplifier. And here's one example here. Here we have the diode reverse bias. You see the plus is here, and this is the photodiode. The other one is also reverse bias. This is the output side, which is isolated. This is the LED. Now here we have a feedback in which the light is affecting the current of this primary diode and stabilizing, in fact, this current. I'm going to analyze it in the next few slides. And then, since the current here and current here are the same, then we're going to get an output which is related to the input, the fixed ratio. Here is another arrangement based on the current source. So we have here the photodiode here and here clamped to this voltage here, and this is clamped to the voltage here. So the current here and here are supposed to be the same because they receive the same light, or the same ratio of light, I should say, from the LED. And then therefore the output again will be a function of the input in a linear fashion, and I'm going to analyze it in the next slide. So here's the photoconductive arrangement. Now we have here feedback within the primary such that the current here of this diode will force this point to be equal to the input. So therefore the current times the resistance is the input voltage. So this is actually setting the current of the diode at the primary. And since the same light is going to the secondary, or a fraction of the same light going to the secondary, we're going to have a current which ideally is exactly like the current at the primary. And then the output voltage would be this current times this resistor. So output is this current times this resistor. The input is this current times this resistor. The currents are the same. So therefore, this is the ratio. However, in this case, the direction of the current is this way. So therefore, we have a negative output. I don't know why they put it here. Very strange. I think it's a mistake, an error. Anyhow, if you like to have the same polarity, then you have to have here a follower, not an inverter amplifier, an inverting amplifier. So here it is, and rather than having it this way, if you have it this way, then again the same current times R2 is the output, and this, therefore you have the same ratio, except it will not be with a minus. Now the better solution in terms of linearity is clamping the diodes, the photodiodes. Here it is clamped to the input here. Here it's clamped to the, again, input here on the secondary side. Currents are the same. So the current times R2 is the output voltage, and the same current supposedly times R1 is the input voltage. So again, we get R2 over R1. So we have built a linear amplifier around this unit, this device, based on the assumption that the current of the two diodes is exactly the same. And also, it remains the same over temperature. This is the assumption here for getting a linear amplifier and a temperature-independent behavior. Now, in reality, the ratio between the diode current and the current through the LED of the primary and secondary is not constant. There's a K1 and K2, and they are also temperature-dependent. But this is not that important. What is important is the ratio between K1 and K2, or K2 over K1, and that is the ratio between the diode. This you like to be 1, stable and temperature independent. If this is 1, then you will get a linear amplifier with a fixed transfer ratio. In reality, the K, the K3, the ratio between the two, K1 and K2, is excellent in terms of temperature stability. This is the 0.005%, whatever, per centigrade. So you see that it does not change. This is a very good behavior. Temperature does not affect it, but this is normalized. The actual number of K3 varies a lot between units. That's very much. It's like, depending how you calculate it, something like 50%, okay? So it's a lot. So this is you get a unit, and then the gain could change by up to 30% in this case. Some companies, like Vishay, are actually supplying units which are pre-selected. So you get a K3 between, say, 0.765 and this 0.859, or this range here. And it turns out that the spread here is something like 6%. So the best you can do in terms of building a linear isolated amplifier is to have an accuracy of absolute accuracy of 6% between input and output. The gain, of course, depends on the ratio of the resistor. Then you have, of course, the accuracy of the resistor. I'm not talking about that, but the unit itself has a 6% error, plus minus 12% overall, which in some application could be okay, some may not. In some application, you can actually do a calibration in the system, and once you do it, it's okay because the temperature dependent is pretty good. Okay, so what is bad is that from unit to unit, you can have up to 6% deviation. Now, some of the companies in their application note, like ITIS, which I guess is now Little Fuse, and then other companies are showing something similar, are showing how you can use this particular unit, the linear amplifier, as a feedback in the power supply. Okay, so here we have an isolated power supply. We have two grounds here. We have an output, and then we have here this isolated amplifier. Now they are showing it in a different way, that the output has no amplifier, just the diode and a resistor without buffering with a operational amplifier, which is okay if it goes into high impedance. So you really don't need an amplifier in this case. So the idea is to put this here. So here is the DC output. This is the DC output. And here it goes into the, I guess, controller. This is a very, very bad solution. It is outrageous how bad it is, in fact. And let me explain why it's this. Now, the conventional solution that usually is used in the design of just about any isolated power supply is the following. We have the output, and then on the secondary side, we have a compensator, which includes the reference here, and then we pass through an isolation barrier to the control. Now, a good choice would be like using an amplifier here or the NT431. I'm not going into the details of the design, and then just a simple optocoupler, and that's it. This is the conventional approach. So this is this approach. We have the output. We have the reference at the secondary side, which we compare to the output. Then we have an amplifier and a compensator. And then the error is passing through the isolation barrier. What is suggested in this application note that I've just shown is to first transfer the output, and then in the primary side to have the reference and the compensator, etc. So let's now analyze what's the difference between these two. To do this, I'm describing these as a feedback system, okay? So this is the conventional one. We have the output compared to a reference. We have here a gain, and then we have the isolator, which is passing the error. Here, we have a isolator passing the output, and then we have the reference and the compensator. Now the transfer function of this unit here, between here, reference, and the output, is the gain, overall gain. This is the overall gain, this part, and this part, divided by the loop gain, which is the same. It is the loop gain. So when the loop gain is much larger than 1, the transfer function is 1. And you can explain it intuitively, very simple, because if the loop gain is high, then the difference between this reference and the output, which I have not marked here, will be very small, okay, because the gain is high, so the feedback will force the output to be very close to the reference, so you have a good tracking, okay? So this is the case here. Now what happens here? If I take the transfer function between the reference and the output, I have the gain here is these two units, P times C, and then the loop gain is the whole thing, including the isolator, here it is. So at high loop gain, 1 drops, and we are left with 1 over isolator, which means that there is no real good tracking of the output of the reference, but in fact within an error of this isolator. So if the isolator is perfect, no problem at all, then you are fine. But if you have any problem with the isolator, some error or temperature dependent, in general I'm speaking, then you are in bad shape because you are not tracking the reference with the output. You are tracking the reference plus the isolator. Here, the nice thing is that this isolator doesn't have to be linear or stable because it is part of the total gain. So usually you have a very large gain, and if the gain is changing a bit due to the isolator, does not matter. Okay? Well, the effect is very small. So this is the correct solution. This is a bad solution. Not only that, it's more expensive because you have to have here a very, very good isolation amplifier. While here you can get by with a simple optocoupler. So what are the conclusions here? Now, linear optocouplers can be used to build an isolated amplifier, no question about that. And it has a very good temperature stability. But the accuracy between unit to unit, the spread, is up to 6%. Some cases it's okay, some cases you can calibrate it, but then you have to build it with the amplifier, etc. Now you can buy a unit which has everything in it, including this optocoupling transfer by light in the unit itself as a linear amplifier, or you can buy this unit and then build your own. Now, I would think that you won't save that much money if you build your own rather than just buying a linear isolated amplifier. Now, the competitors, of course, to this whole thing are the isolated amplifier that could be less expensive, and in the case of a power supply, you really don't need a linear amplifier. You can get by with the regular optocoupler. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.